Recording is rolling. Welcome to a new week, a new topic. We're going to take a few weeks to cover forces. This is a dynamics, which is unit 2 and by the AP book, or in your textbook it's chapter 4. Right. So you guys just turned in your kinematic quiz, take-home quiz from the weekend. So thank you. Let me talk a bit about this stuff. Some assignments coming up. So you may have known, I don't know if you kept an eye on Google Classroom over the weekend. You probably saw that I posted a ton of documents. Now, I was here at the school over the weekend. I was going to print out a bunch of papers and give it to you today, but every single printer was broken. So, sorry, I can't do that right now, but anyway, I'm going to get some papers to you guys. Some of those are going to be, it's just the stuff that's already posted on Classroom if you want to take a look at that. All right, so your next traditional homework is going to be due a couple weeks from now. So this is not this coming Friday, but next Friday. And it's these problems out of the textbook, these 8 problems. Now, just like last section, I'm going to cover some very similar type ones in class. So as long as you're following along, you'll be all right. Okay. I've also got a bonus homework for you guys. I think this solves the problem that I was trying to sort of do all along. And then this idea came to me like, oh man, this is perfect. This is exactly what I did. So I've already created a column and focus for this. Now, yeah, thank you. Right, so this is an optional homework. I probably won't have. I'll probably run out of time before I get to do as many problems as I would. I could just stand here all day and do a bunch of problems with you guys, but I just got to do lots of other type of activities too. So if you do these extra problems and turn those in, then I will give you those points, but everybody's starting out by default with an exempt grade. Right? So if you don't do them, then don't worry about it. But if you do them, then you'll get some extra points. Yeah, I think this is a much better system than the one I had before. But here's up. Also, since you guys are AP Classroom Unit 2 multiple choice has been open for a while, so that'll be due. This particular date, 9/27, is a Monday, and then we'll do what we did before. So I'll take a day to go over those. Right? Any questions about these assignments? Okay, so traditional assignment, got a bonus assignment that you're exempt from unless you want to do it, your points, and then AP Classroom. Okay, so let's take a look at, you guys see some new posters hanging around my room. Now, I just wanted to go through these real fast, just leak through these. You guys can get a look at these. Yeah, right?
Is the bonus homework also due on the same day as the regular?
Yeah.
Okay.
Yeah, so yeah. All right, so I won't go through these in a whole lot of detail, but some of the notes that I give you guys in the coming weeks, you guys are going to see these, so let's just glance through these. Other thing I want to mention is, I know I didn't realize this until after I hung them up, but I see that if you're sitting in the back of the room, some of the font's kind of small, so I do encourage you guys at some point to get a closer look, maybe take pictures, but these will be some of your notes anyway, eventually. So here's Newton's laws of motion. Just 3 laws of motion that govern everything in the universe, has to do with forces. So there's law of inertia. There's this really short formula, F equals ma, that by itself is a law of motion. And then there's the equal and opposite rule. For every force, there's an equal and opposite reactive force. You guys probably learned these maybe in middle school. So just coming back. Right. By the way, our new variable in unit is force, which is measured in newtons. You guys are going to get your hands on some spring scales today. So if you put a force on it, force is just a push or pull. The spring scale will tell you how many newtons of force that is. Again, I'll give you guys notes and more details in the future. Okay. Hey, you've seen this before. Look at this. I got a weight on an incline, right? Like a block on an incline. I bet this is its weight vector straight down. That's the type of force split into components. Now, I've also gone back and added more to the story. So these vectors are also part of the story. We'll talk about this later. What you're looking at right here is called a free body diagram. So it's just a diagram that has all the forces labeled. There's a certain way to put them together. I'll talk about that more in the future. Here's a guy standing on a planet. He's got some weight pulling him down. That's how I'm going to represent weight. Mass times gravity, free fall. So remember that Newton's third law of motion, for every force, there's an equal and opposite reactive force. Does the Earth pull you down? Are you pulling the Earth up with the same force?
No.
Equal. For every force, there's an equal and opposite reactive force. Right? We're going to take a look at some elevators at some point. You could be accelerating up in an elevator or accelerating down in an elevator. Right? There could be some free body diagrams for that. Do a little bit of math on the side, some shorthand equations that can help you out on the AP exam eventually. Ooh, Atwood machines. Some point I'm gonna have you guys do a lab that looks like this. In fact, if you want to get head start, if you finish today's lab a little bit early, I did throw some red pulleys back there. There's some red pulleys. There's some string. There's some of these lab weights. What would happen if you take a couple lab weights, throw them, hook them in a string, throw them over a pulley? What would happen? How would that system accelerate? I bet if they were the same weight, I bet it wouldn't accelerate at all. I bet the more weight you put on one side, the more it's going to accelerate. Right. You can also modify this output because this is called an Atwood machine. It looks like, sometimes I refer to this as a double elevator Atwood, but you can also modify it. What if you just have one pulling down and one being dragged horizontally, something like that? Now, I do want to have you guys eventually also rig this up in a lab situation. And if and when you guys do that, I usually have you guys put a Hot Wheels card underneath this one to create a low friction environment. Okay, so it just like slides along, right, like that. Okay. Yeah, and you guys are seeing force vectors on all these diagrams. Okay, so that's all the new posters. Like I said, I'm going to give you guys notes on all those in the future and go into much more detail on those. But just glance at those just so you can become familiar with them. Okay. Oh, I've got a puzzle cup for you guys to think about. So I'm going to bring this in. And so, hey, look at this. This looks just like a normal cup. Yeah, I would buy this from a store. It's all hot glued together, all rigged up. Like, I don't know where it's right. But wait a minute. Is that a hole in the bottom? Is there a hole in the bottom of this cup? This is a trick cup. What's that? Straw hole on that side? Huh. What? You see a hole in the bottom, right?
Yeah.
Yeah. Huh. I wonder if this even holds water. We're going to find out. Please work. 50-50. Come on. All right. Hey, this cup looks slightly different, but it's my backup cup. And it is holding water. It's not a trick. It has a straw hole. It's everything. Just sometimes gives me trouble. Right, so, yeah, I see. Okay, so I do see that it holds water. It holds water like halfway, right? Let me give the other one more go. Because if I can get this to work, it actually is. Oh, okay. Never mind. Let's go back to the original cup. This cup actually works better if I can get it to work. Right. So you do see the original cup is holding some water, right? So it's halfway filled with water. Right. All good. Well, maybe it's just a normal cup. It holds the water. I'll find again. Give me more water. This goes back thousands of years, by the way. So, okay. So some of you guys might know this. Right. I don't want to tell you what it's called in case anybody just like Googles the answer.
I remember what it's called, but I know.
Yeah. Anyway, you guys told me fill it to the brim, and now all the water's leaking out. So hold on a minute. I filled it up halfway with water. It held the water perfectly fine. I filled it all the way, and now what? It's just going to leak out. And you know what? It's almost finished draining here. Let's just wait for it to. Oh, all right. So now all the water drained. Let me bring this back over so you guys can take a look. Hey, all the water drained. Well, there's a little trickle of water at the bottom, but basically it all drained. So let me draw you guys up a diagram. Recap of what just happened. Show you guys a cross section.
No.
Right, so showed you guys the cup. There was some kind of hole there, some kind of hole here, some kind of straw connection maybe. I filled it up halfway with water, and the cup held the water perfectly fine, no problem. Then I filled it to the brim, and the water was draining out the bottom. Okay, so why would it do that? But then here's the other like weird spin at the end is that the water level didn't just go back to the previous like halfway level, that it was perfectly fine holding before. In fact, the entire cup drained, and now you have an empty cup. So question for you guys is, how are these straws connected on the inside? How are the straws connected? Yeah, okay, so some of you guys are actually familiar with this, so awesome if you are, but everybody else, I'm going to give you guys probably at least a day or two to think about that. I'll come back to that later this week. Okay, so any questions so far about anything? Right, so let's get to today's actual, hold on a moment. Oh, here we go. Right, so let's take a look at these spring scales in this page. So here's how this is working. Remember I told you guys the copiers were all broken this weekend. So I had to print these off at home, which means that I've only got enough for one per group. So here's how we're doing this. You guys are gonna have to share a lab page, and you can all put your names on it. So whoever's in a group, just put your name on the paper. Okay, there could be a few names on it. Okay. And this is really like 10 mini labs. There's no AP write-up with this. Okay, this is just exploratory. This is kind of like a structured sandbox sort of thing. And all I want you guys to do is to get your hands on these spring scales, these weights, and to try out each of the things that I tell you and record the data that I want you to record. So you can really get a feel for what's really going to be a setup for a lot of problems that we're going to be solving in class. Like, what happens when you put it in this Y shape and you spread it out and make it more like a T? What happens when you put it in a chain? What happens when you connect it with a string and just start pulling it back and forth? What does this look like? Other detail I want to mention is that these springs have different stiffnesses and they're color coded. So the green ones have almost no stiffness. They can read up to 5 newtons of force. That's where they're maxed out. They can only read up to 5 newtons of force. Okay? And it's really small stiffness, so barely any force at all, and it stretches really easy. Okay? That's called a very small spring stiffness, or a very small spring constant. Okay? The brown ones are pretty versatile. They're kind of in the middle. They can read up to 10 newtons. Ooh, I can definitely feel that's a bit stiffer. Yeah, it's about twice as stiff. Read up to 10 newtons. The white ones are a bit stiffer than that, and then the gold ones, these read up to 50 newtons. You can feel this, lots of force, just to pull this thing. Guys, like that sound fit? They can help add to the auditory experience. So you guys got those. You guys got some lab weights. Now, just get in groups. Again, this is very like sandbox lab exploratory kind of deal. Just pop this in the grade tray at the end of class, which you should have time to do as long as you keep a good pace, and you are good to go. I'll be walking around helping you guys out.